Welcome to The Explainer. Today, we're diving into a real chemical detective story. We're going to synthesize zinc chloride and figure out its hidden mathematical fingerprint. It's a classic lab experiment, taking raw, highly reactive materials and distilling them down to a single elegant chemical formula. It's this fascinating journey from the physical world of bubbling acids straight into the abstract world of chemical math, all through the lens of quantitative analysis. Here's our roadmap for today. We'll start with the chemical composition mystery, get our tools for the job, run through a pretty volatile procedure, weigh the evidence, and finally, crack that formula unit. All right, Section 1, the chemical composition mystery. Let's figure out what we're actually looking for here. Think about it. Every compound has a unique identity, right? It's like a molecular barcode. But how exactly do chemists figure out those precise, hidden mathematical ratios of elements inside a newly synthesized substance? When you mix two things together and create something entirely new, nature doesn't exactly hand you an instruction manual with the chemical formula printed on it. We've got to derive it ourselves through careful, calculated observation.
And that all comes down to the formula unit. It's the absolute simplest ratio of elements in a compound, which we figure out through quantitative analysis. So let's say you analyze a mystery compound and find it's got exactly 0.1 moles of silver and 0.1 moles of bromine. Well, they exist in a perfectly balanced 1-to-1 ratio, so the formula unit is simply AgBr. Today, our mission is to determine the formula unit for a compound made of zinc and chlorine. By tracking the starting mass of our zinc and eventually calculating the final mass of the chlorine it bonded with, we can get that percentage composition and totally deduce our formula.
Moving right along to Section 2, tools for the job. Because before we can solve anything, we need our gear. Our apparatus and chemical reagents are actually pretty straightforward, but they definitely demand extreme precision. We're using a 50 milliliter crucible, which is going to act as our main reaction vessel. And we strictly handle this with tongs, right? We don't want any contamination from the oils on our skin. And analytical balance is absolutely critical here to weigh our fine zinc powder down to the exact decimal. We also need a hot plate, a glass rod, a measuring cylinder, and our two key players, about 0.25 grams of zinc powder and 6 molar hydrochloric acid, or HCl. Okay, lab is set up. Let's get into Section 3, a volatile procedure. Time to initiate the reaction. Following Step 3 of our manual, the physical reality of chemistry really comes to life. We carefully add 10 milliliters of that 6 molar HCl to our zinc powder and just give it a gentle stir. Now, we aren't just mixing powders here. We are kicking off a vigorous chemical reaction. The zinc is actively being consumed by the acid, and it's releasing hydrogen gas in the process. You can literally see the reaction bubbling away right there in the crucible. Which brings us to a massive safety warning. Wet hydrogen gas can cause explosions. Yeah, that's not just a casual disclaimer. Hydrogen gas is highly flammable. Because of this volatile byproduct, this entire interrogation of elements has to happen securely inside a fume cupboard. Keep it far away from any open flames or sparks. Safety first, always. Now, what's really interesting is the contingency built into the method here. Not all reactions go perfectly on the first try, do they? If we look at the crucible and see the zinc powder hasn't fully dissolved in that first acid bath, we don't just dump the whole bottle in. No way. We carefully add more acid in highly controlled 5 milliliter increments. We have to continually monitor the dissolving process, making strictly sure we never exceed a total of 20 milliliters. We want just enough to dissolve the zinc without flooding the whole sample. So, once the zinc is dissolved, we have to isolate our newly formed compound by removing the liquid. And notice the strict contrast between the heating and cooling phases here. During the heating phase, we have to heat the crucible super slowly on a hot plate. Why? To avoid splattering. If even a tiny droplet of our compound splatters out, our final mass is ruined and the whole mathematical formula is corrupted. We also have to take it off the heat immediately once dry so it doesn't melt. On the flip side, during the cooling phase, we must cover the crucible and let it sit until it hits room temperature. It's two entirely different types of thermodynamic control, and they're both absolutely vital for accurate data. With our compound fully dried out, we transition to Section 4, weighing the evidence. Time to gather our numerical clues. To ensure absolute, undeniable dryness, the procedure dictates this really rigorous loop. Listen, water weight is the enemy of quantitative analysis. If there's even microscopic moisture left in that salt, it's going to read as extra mass and completely throw off our formula.
So we have to heat the crucible, let it cool to room temp, weigh it, and then do it all over again. A first heating, a second heating, and quite often a third heating. We keep running this repetitive cycle of heating, cooling, and weighing until the difference in mass between consecutive weighings doesn't exceed 0.02 grams. I mean, think about how incredibly precise that is. 0.02 grams is practically the weight of a grain of sand. When the scale finally stabilizes within that microscopic margin, we know for sure we've eliminated all the moisture. We finally have our pure, unadulterated evidence.
All right, let's take that perfectly dried evidence over to Section 5, cracking the formula unit. Let's do the math.
We structure our findings systematically by logging our initial clues into the first rows of our data sheet. We record the exact mass of the empty crucible and the mass of the crucible with the raw zinc powder. Then, just by subtracting row 1 from row 2, boom, we get row 3, the exact true mass of the zinc powder that went into the reaction.
And this brilliantly illustrates the entire purpose of a lab experiment. It's like a giant puzzle coming together. You've got the physical steps from the procedure manual, the pouring, the heating, the weighting. Then you have the data sheet. Every single physical action you took directly populates the ultimate calculation rows. The physical world translates perfectly into cold, hard mathematical data.
So here's how we cross the finish line. Step 1, we take the absolute smallest final weight from our heating cycles, because the smallest weight represents the driest sample, right, to find the total mass of our synthesized zinc chloride. Step 2, since we already know the starting mass of the zinc from earlier, we simply subtract that from our total zinc chloride mass. The difference? That is the exact mass of the chlorine that was pulled from the acid and bonded to the zinc. And step 3, with the mass of both elements in hand, we convert them into moles, find the simplest ratio, and officially determine the formula unit. The mystery is solved.
But hey, before we officially close the case file on this experiment, the manual gives us 3 crucial discussion points to really test our understanding of the chemistry. It asks us to explain why we never weigh the content while it's hot, which actually has to do with convection currents messing with that delicate analytical balance. It asks us to write out a balanced equation for the reaction. And finally, it asks about that cooling process.
Which leads me perfectly to my final point. I'll leave you with this provocative thought to ponder about our methodology today. Knowing what you now know about the absolute necessity of keeping moisture out of our final compound to ensure our mathematical ratio is absolutely perfect, why exactly must that crucible remain covered while it cools down to room temperature? What invisible variable in the laboratory air are we so desperately trying to keep out? Think about that as you reflect on the incredible precision required to uncover the hidden mathematical secrets of the chemical world.